Hi there. Welcome to this first part introduction of a series of videos about measurement and analysis of tandem solar cells. Without further ado, let's get into it. How a tandem solar cell works is that instead of using one type of semiconductor to absorb as much of the sunlight as possible, it relies on two active semiconductor layers, one with a higher band gap, called the top cell, that makes more efficient use of the shorter wavelength portion of the sun's spectrum, and another with a lower band gap called the bottom cell that makes more efficient use of the longer wavelength portion of the spectrum. This way, the overall energy conversion efficiency is substantially higher. While this principle has been demonstrated, and even more efficient cells, made of not two semiconductors, but three or more active layers have been made using 3,5 compound semiconductors. They were also orders of magnitude more expensive to fabricate. It is only in the last decade that perovskites, a class of material that can be solution processed and cheaply fabricated, has emerged as a promising candidate to be used as a top cell in a cost-effective tandem device, with traditional silicon making the bottom cell. The potentially low cost and high efficiency of the perovskite material and the mature silicon technology that enjoys vast economy of scale makes a very compelling case for a commercially viable, mass-produced tandem cell. This is what's getting the photovoltaic R&D community excited and driving a lot of research around the world today. A tandem solar cell made of perovskite and silicon uses the perovskite layer as the top cell and the silicon material as the bottom cell. One cost-effective approach to fabricating it involves simply applying the solution processing steps to build the perovskite active layers directly on top of a finished silicon solar cell. The resultant combined device is also called a two-terminal device because a series electrical connection is formed between the top and bottom cells during fabrication. Electrically, it can be represented by a simple circuit model that consists of top and bottom cell circuits hooked up in series. Each of the top and bottom cells have their own current source that represent their respective photoabsorption processes, diodes that represent their recombination processes, and shunt resistors where there is undesirable current leakages. We can represent their combined series resistance by the resistor up at the top. Ideally, the shunt resistors should be infinite, representing the case of zero current leakage, and the series resistor should be zero, representing zero ohmic losses in the electrodes and materials. The current sources should ideally be close to being half of what can be harnessed from the sun's spectrum for light with energy higher than the bottom cell's band gap, and the diode's dark current densities should be as low as theoretically possible to minimize recombination losses. The equivalent circuit model of the tandem cell is a useful representation that allows us to understand what are the limiting factors, be it the absorption, recombination, shunts, or series resistance losses, to device efficiency, offering us guidance on how to improve and optimize the device. But it can also be hard to infer the values of the circuit elements from measurements when there are so many of them, especially in a two-terminal device where the top and bottom cells are inseparable and their circuit model elements cannot be probed in isolation. So it's especially important to have a measurement and analysis routine that is good at separating out these circuit elements, for one to have a clear picture of the device properties and how to improve them. Now for a tandem solar cell, there are three knobs that can turn to put the cell into different operating points for measurement. Namely, these are the intensity of short wavelength light that is absorbed by the top cell, the intensity of long wavelength light that is absorbed by the bottom cell, and the electrical voltage applied or current injected into the device. Using these knobs, one can probe the device under different conditions to get responses that reveal its different parts. But the interpretation can be difficult. While in our next video we will dive deeper into the various measurements one can perform on the tandem cell, here it suffices to say that they produce lots of measurement results that are hard to analyze just by looking at them. These measurement results consist of various currents, voltages, IV characteristics, as well as luminescence images. How do we go about interpreting all of them to elucidate the underlying properties of the tandem solar cell? One flexible and automated way to interpret data is by model fitting. The circuit model serves as a very good basis for this exercise because it has the ability to simulate the device characteristics, namely the current and voltages, when given the circuit element values and the boundary conditions like the applied voltage. Conversely, An iterative routine can be performed by tuning the circuit element values until the model is able to simulate results that match with experimental data. Here we briefly show the fitting iterations as well as the circuit parameter of best fit. Afterwards, one can also do some sensitivity analysis to determine if the solution fits uniquely well to the data. All non-imaging data, like IV characteristics and voltage measurements, can be explained using the circuit model. Imaging data contains spatially resolved information and describe the non-uniformity of the solar cell. In order to interpret these images, one has to go beyond the simple circuit model and make use of simulations that resolve spatially varying properties. One such representation is the finite element model, like Griddler, which approximates the continuous surfaces of the solar cell as triangular meshes. Griddler has the ability to simulate the spatial distribution of cell voltages, and thus can be used in a fitting routine to find the underlying spatially varying properties of the tandem cell that is consistent with the measured image patterns. One can see here that, upon completion of the fit, Griddler reveals the underlying areas where the interface contact resistance is high, as well as areas where the recombination rate in the top and bottom cells, respectively, are high. One can also double-check by simulating the luminescence images and making sure they match well with the experimental images. Being able to explain imaging data with spatially resolved underlying properties can help researchers pinpoint problems related to fabrication and devise ways to improve it. In summary, today we've introduced a measurement and analysis workflow for tandem solar cells that consist of using the equivalent circuit model to fit to electrical measurement data, and then the finite element model to fit to imaging data. The two methods are not exclusive to each other. Rather, they work very well together, as the circuit model is fast and can generate a very good first approximation of the tandem cell as a uniform device, passing the best fit parameters to the finite element model for a subsequent fit of the spatially resolved cell properties. In the next videos, we will cover in greater detail the different kinds of measurements, the Python program behind the circuit model fitting routine, and then also an under-the-hood view of how the finite element model fit works. I hope you've enjoyed this video. See you next time.